Hello, good morning. My name is Nurul Atirah Farihan. We're from Group 16. In this video, we're going to show how we use derivatives in analyzing environmental feature in UMK Jeli campus. For the first part, my problem, I'll monitor land slope erosion around the campus. When it rains heavily, soil erosion may occur. So to identify risky areas between the slope, we use derivatives. As shown above is the function for the soil erosion. In this equation, x represents horizontal distance from the base, while fx represents height of each point. The derivatives of the function is as above. The derivatives tell us rate of change of the slope at any given height of the hills. Now, let's calculate the slope at x equal to 10 meters. By substituting x equal to 10 into the derivative, we will get f prime 10 equal to negative 0.03 multiplied by 10 to the power of 2 plus 0.4 multiplied by 10 minus 0.5. Then, we will get negative 3 plus 4 minus 0.5. The last answer will be 0.5. So, the slope at x equal to 10 meters is 0.5. So, when x equal to 10, the slope is 0.5. This indicates gradual slope at that point. In conclusion, derivatives helps to monitor slope erosion in the Jeli campus. Thank you.
Hello everyone, my name is Imam Hafiz. In this segment, we're going to discuss how to maximize capacity sit at the cafeteria area the Jeli campus. Our task is to figure out how many tables and chairs should be placed to maximize the number of seats. This is a problem that we will function to model the situation. First, let's start defining some variables. Let's define the first given by a chair with the number 1. After defining some variables, we need to calculate the total area used by the tables and chairs is given by the constraint. How are you going to calculate? We're going to calculate like this. 10x plus 2y equal to 300. We can rearrange the equation to express y in terms of x. Y equal 150 minus 5x. Now, we know the total number of seats, P times X, is simply the sum of the number of tables and chairs. We're gonna put it as P times X equal X plus Y equal X plus, in bracket, 150 minus 5X equal to 150 and minus 4X. This is a linear function, but we want to approximate the problem using a quadratic function. So let's modify it slightly by introducing a quadratic term to better model the seating capacity. We will approximate P times X as equal to minus 4S plus X2 plus 150. Now, we have the quadratic function that we can use to find optimal number for the table. To maximum seating capacity, we need to find the critical points of this quadratic function. As shown above, we differentiate the equation and we will get this. Okay, we set the derivative equal to 0 to find the critical points. And we can get x equal to 2 as you can see. To verify if this critical point is a maximum, we take the second derivative of p times x. The second derivative is, since the second derivative is positive, this means x equal to is a local minimum, meaning the seating capacity decreases as we increase x. So the optimal number of the tables must be at the boundary. Now, let's check the seating capacity at the boundary, values of x. When x equal to 0, meaning there are no tables and only chairs. That's make p times 0 equal to minus 4 times 0 plus 0 power 2 plus 150. It's make to 150. When x equal 30, meaning there are 30 tables and no chairs. When we calculate, it's gonna be like p times 30 equal to minus 4 times 30 plus 30 power 2 plus 150 equal to minus 120 plus 900 plus 150, and we're gonna have 930 at our result. So after analyzing of quadratic, model and derivative, we find that optimal seating configuration that we can put is we don't have to put no tables. So the total seat we're gonna have is 150 seats at that cafeteria. Well, that's all from me. We can continue with my friends.
Hi, my name is Nur Aida Usna binti Taib, and my problem is waste management in event at Jeli campus. To know more about my problem, let us investigate one of the event that happening at this campus. As we all know, a large amount of student can generate a significant amount of waste in this event. I'm going to show you how we are managing waste using derivative to predict waste generation of rate. We could model the rate of waste generation in this event as it shown here. As it shown here, we are generating 5 kg waste per hour, and the rate increased by 2 kg per hour as the event goes on. So, the longer the event was, the large amount of waste produced. Let's calculate the total amount of waste generated during the 3 hours event. This is the formula to calculate the total waste. Now, substitute the function into the formula. Let's solve the integral first. The integral of 5 plus 2t can be calculated by term. 5 plus 2t dt equals to 5 dt plus 2t dt. So the answer becomes 5t plus t to the power of 2. Now substitute the integral into the formula. Substitute t equals to 3 and it becomes 5 multiplied by 3 plus 3 to the power of 2 is equal to 15 plus 9, and the answer is 24. Now substitute
t equals to 0, and it becomes 5 multiplied by 0 plus 0 to the power of 2, and the answer is 0. Now we combine it together and it becomes w3 equals to 15 plus 9 minus 0. The final answer is 24.
So in total, we expect 24 kilogram of waste to be generated during this 3-hour event. By using this calculation, we can know how much the waste generate in any event in this campus. That's all from me. And to know more about the derivative in our campus, I will let my team member to explain his problem statement. Thank you.
Last but not least, me as the final member of the group would be presenting how derivatives are applied on environmental monitoring, specifically on vegetation growth around our campus. As you can see, our campus is rich in biodiversity, therefore it requires careful observation to ensure a precise or better land management. Thus, by using derivatives, we can be able to predict and measure the changes in vegetation, which enables us to act proactively against environmental degradation. As for your information, vegetation cover is vital to regulate our ecosystem, preventing erosion and also supporting local wildlife. However, factors like deforestation and climate change tends to reduce this cover. Thus, to monitor these changes effectively, we come out using vegetation area as a function of time using derivatives. To investigate further about my problem statement, let's consider the vegetation area in square meters by this equation. As you can see, the equation is shown on the screen. Here, 1000 represents the initial vegetation area. Meanwhile, the 50t represents models the annual growth, and the negative t square accounts for degradation over time. Next up, to pursue with our calculation, we can use derivative to calculate the growth rate in the plantation. As you can see, the formula for the growth rate is shown here. What could we do regarding this formula? Easy. We can first of all, we have to interpret this formula. How could we interpret it? It's very simple. So when we get the growth rate is more than 0, it means the growth rate is increasing. When the growth rate is equals to 0, that means the growth rate has reached its peak. And when the growth rate is less than 0, that means the growth rate starts to decrease. Regarding the interpretation we did just now, we could find out that how fast vegetation increases or decreases in a span of time. For example, when we use the same exact equation and we set it to 0, we find out that it reaches its growth peak at about 12.5 years. When it is at its peak, the vegetation area covered is about 1312.5 square meters. After this, the vegetation is said to undergo a certain decrease due to certain environmental factors. In conclusion, derivatives provide a powerful tool in environmental monitoring. By using this approach, our campus could provide a more sustainable land management and biodiversity conservation. With the end of that, I guess it sums up my problem statement on growth rate using derivatives. That's all from me. Thank you.